Imagine standing deep within the heart of an ancient pyramid, surrounded by millions of tons of precisely cut stone, and suddenly realizing something that defies all logic. The builders who created this marvel intentionally designed weak points into its very framework, places where the structure could be brought down. It sounds like a contradiction, doesn't it? Why would any civilization pour generations of labor, resources, and ingenuity into constructing something magnificent, only to engineer its potential collapse? This isn't a design flaw or an accident waiting to happen. It's a deliberate, sophisticated choice, one that unravels everything we thought we knew about ancient engineering. From the shadowy chambers of Egypt's Great Pyramid to the step temples of the Maya, and further still to the sprawling complexes of the Roman world, we find evidence of this puzzling practice. Structural vulnerabilities that appear at first glance to be errors now emerge as calculated features, planned fracture points, strategic material selections, and architectural decisions that guided how these buildings would fail, transform, or even destroy themselves under the right conditions. These collapse points weren't oversights. They were baked into blueprints that balanced physical durability with spiritual necessity, practical function with profound symbolism. Today, we're setting out on a journey to explore one of history's most intriguing architectural mysteries. We'll venture beyond the surface of ruins and relics to uncover the startling reasons why ancient builders embedded intentional weakness into their greatest triumphs. This is more than a story of stones and mortar. It's a window into how ancient societies saw their world, its cycles, its dangers, its gods, and its future. Together, we'll decode the hidden logic behind these engineered failures and discover what they tell us about humanity's enduring desire to build not just for today, but for eternity, on our own terms. It forces us to completely rethink what we mean by a flaw. To our modern eyes, trained by centuries of engineering that prioritizes unyielding strength and maximum longevity, a crack in a load-bearing wall or a section built with intentionally weaker materials looks like a mistake. It signals a failure of design, but through the lens of ancient wisdom, that very same crack might be a masterpiece of foresight. These builders weren't trying to create monuments that would remain forever frozen in time, untouched by the hands of change. Instead, they were designing dynamic system structures that could interact with forces like earthquakes, ritual practices, and the passage of centuries in a controlled, predictable manner. They were building in 4 dimensions, with time itself as a core component of their blueprint. Imagine the mindset required to deliberately incorporate a point of failure into your life's greatest work. It speaks to a humility and a profound understanding of natural cycles that much of modern construction has left behind. We build to resist nature, they often build to collaborate with it. This philosophy required an intimate knowledge of materials, physics, and geometry that we are only now beginning to fully appreciate through advanced forensic archaeology. By designing a structure to collapse in a specific way, say, for one chamber to implode while leaving an outer shell intact, these engineers demonstrated a grasp of load distribution and structural dynamics that is incredibly sophisticated. They weren't just stacking stones, they were programming a building's behavior for centuries to come. This revelation turns archaeological interpretation on its head. A pile of rubble in a specific location within a ruin is no longer just evidence of decay. It becomes a clue, a signature left behind by the original architects, telling us exactly how they intended the building to transform. It means that when we look at these ancient sites, we're not just looking at what was built, we're looking at a set of instructions for what it was meant to become. To truly grasp the radical idea of building intentional weaknesses into sacred or monumental structures, we need to step outside our modern engineering mindset. Today, we compartmentalize. An architect designs the form, an engineer ensures it stands, and the meaning is often an afterthought, added as decoration. For ancient builders, this separation simply didn't exist. Their approach was profoundly holistic, weaving together threads of astronomy, mathematics, religion, and raw practical experience into a single, unified fabric of creation. A pyramid wasn't just a tomb, it was a machine for the pharaoh's ascension, an astronomical observatory, and a representation of the primordial mound of creation. A Maya temple wasn't merely a platform for rituals, it was a physical manifestation of sacred mountains and the cycles of time itself. In this worldview, every stone, every angle, every proportion was charged with meaning. A structural beam was also a spiritual conduit. A load-bearing wall was a cosmological map. This changes everything. What we might label a flaw from a purely structural perspective could, in this integrated system, be a critically important symbolic feature. A deliberate weakness might not be a failure to achieve strength, but a successful achievement of a different priority altogether. One of ritual function, celestial alignment, or planned renewal. Their concept of time was also fundamentally different from our linear march of progress. Many ancient cultures viewed time as cyclical, mirroring the patterns of the seasons, the movements of the stars, and the myths of death and rebirth. If time is a circle, then nothing is meant to be permanent in its current state. Everything must pass away to make way for the new cycle. A structure, therefore, didn't need to be frozen in its original form for eternity. Instead, it needed to be capable of transformation, to have a kind of architectural life cycle. Built-in collapse points could be the mechanism for that necessary transformation, the designed moment of death that allowed for a ritual rebirth. This philosophy represents a breathtaking long-term perspective. These builders were not just constructing for their own generation. They were planning for generations centuries into the future, anticipating the need for their creations to adapt, to be renewed, or to be ritually decommissioned. They engineered with a humility that acknowledged their place within these vast cycles, rather than an arrogance seeking to defy them. This deep, interconnected way of thinking, where a crack in a stone can be as meaningful as the star it aligns with, is the essential key that unlocks the mystery of why they would design their own structures to fail. This concept comes alive most vividly when we look at the ancient Maya, whose entire civilization was built around sacred cycles of time. Their long count calendar measured vast epochs, and the completion of one of these great cycles was not just a date on a stone, it was a moment of cosmic significance, a time when the world as they knew it needed to be symbolically destroyed and reborn. To make this metaphysical event tangible, they turned to their most impressive physical creations, their towering temples. Archaeologists have discovered that many of these pyramids are not single structures, but rather like Russian nesting dolls, with newer, larger temples encapsulating older ones. The process of building a new layer wasn't a simple act of addition. It was a profound ritual. Before constructing a new temple over the old, specific passages, doorways, or even entire chambers within the existing structure were sometimes deliberately collapsed. This wasn't haphazard vandalism. It was a carefully orchestrated demolition using precise engineering knowledge. Builders might weaken key support pillars or lintels, knowing exactly how much force would be needed to make a specific section cave inwards during a ceremonial event. Imagine the powerful spectacle. During a great ceremony marking the end of a calendar cycle, priests or rulers would trigger this planned collapse. The roaring sound of tumbling stone, the clouds of dust, would physically represent the death of the old era. This controlled destruction purified the site, making the old temple ritually dead so that the new one could be born atop it. The rubble itself often became the sacred foundation and fill for the next phase, literally building the future from the pieces of the past. This practice transformed architecture from a static monument into a dynamic participant in the community's spiritual life. The intentional weakness designed into a temple's roof wasn't a failure, it was a sacred door, a mechanism for transformation. It allowed the people to physically interact with the cosmic cycles they believed governed their existence, turning abstract belief into a shared, powerful, and unforgettable experience. This deep interconnection between stone and spirit reveals a world where creation and destruction were not opposites but partners in an eternal, necessary dance. Beyond the cycles of ritual renewal, these same architectural principles took on a far more pragmatic and urgent role: defense. Imagine an invading army breaching the outer walls of a sacred complex, their torches flickering against gold-lined chambers filled with irreplaceable artifacts and spiritual relics. In such a dire moment, a seemingly catastrophic design choice could become the ultimate salvation. Ancient engineers, in their profound wisdom, sometimes designed specific collapse points to function as architectural traps, a final, desperate measure to protect what was most precious from plunder and desecration. This transforms our understanding of a structural weakness from a flaw into a sophisticated security system. A single, precisely cut pillar in a tomb might look identical to all the others, but it could be the linchpin holding up an entire section of the ceiling. If that pillar were knocked away or deliberately pulled down by a defending priest or guard, it could trigger a controlled implosion, causing tons of stone and debris to crash down exactly where it was intended, sealing the inner sanctum, burying the treasure chambers, and making the heart of the complex inaccessible and unappealing to looters. This served a dual purpose. Practically, it physically blocked access and hid valuables under what appeared to be random, catastrophic collapse. Spiritually, it preserved the sacredness of a space. For many cultures, the desecration of a temple or tomb by enemy hands was a spiritual catastrophe far worse than its physical destruction. By bringing the mountain down upon their own sanctuary, the defenders ensured that even if the site was captured, its soul remained intact and inviolate, its most sacred mysteries protected by a tomb of their own making. This strategy required an intimate understanding of structural causality. The builders had to calculate exactly which element to weaken so that its failure would produce a specific, localized collapse rather than causing the entire structure to pancake unpredictably. It's a terrifyingly brilliant form of architectural judo, using the immense weight of the building itself against any would-be violators, turning the structure's greatest asset, its mass, into its own best defender. The very vulnerability became a hidden strength, a secret weapon woven into the stones, waiting silently for centuries for a moment of crisis that might never come, yet forever ensuring that some treasures remained forever out of reach. Now consider the silent, majestic dance of the heavens above these ancient sites, a dance so slow and grand that its effects are only noticeable across generations. This celestial movement, known as precession, gradually shifts the positions of stars and the precise points of sunrise and sunset over a cycle of 26,000 years. For cultures that built their calendars, rituals, and very worldviews around these alignments, a temple doorway that perfectly framed the rising sun on the solstice was not just architecturally pleasing, it was cosmologically critical. But what happens when the sky itself begins to drift out of alignment with your stone calendar? This is where another layer of genius in intentional collapse points reveals itself. they served as an ancient form of celestial maintenance. Certain structures were designed not as permanent fixtures, but as adjustable instruments. A specific wall or roof section, carefully engineered to be weaker than the surrounding masonry, could be deliberately dismantled when the accumulated drift of the stars demanded it. This wasn't a repair job born of failure, it was a planned recalibration. The builders understood that their magnificent observatory temples would need periodic updating to stay in sync with the cosmos. By incorporating these designed failure points, they created a built-in mechanism for future generations to make precise adjustments without having to tear down the entire sacred edifice. It's a concept that requires almost unimaginable foresight. They were effectively writing a user manual for astronomical maintenance that would be read centuries later, trusting that their descendants would possess the knowledge and will to perform this sacred tuning. We see potential evidence of this in sites like the Sun Temple at Machu Picchu or certain Egyptian temples, where specific architectural elements show signs of being carefully taken apart and reassembled slightly differently, as if fine-tuning the building's sightlines to a moving target in the sky. This practice transforms our view of these structures from static monuments into dynamic, collaborative projects across time. The original builders and the priests 1,000 years later became partners in a grand, multi-generational endeavor to keep heaven and earth in conversation. The intentional weakness in the stone was therefore a concession to the inevitability of celestial motion, a humble and brilliant acknowledgement that even the most solid human creation must sometimes yield to the slow, majestic turn of the universe. Perhaps the most counterintuitive and brilliant application of these designed weaknesses lies in their potential role as ancient seismic protection systems. In regions frequently shaken by the Earth's tremors, a structure that is completely rigid and unyielding is often a structure doomed to complete and catastrophic failure. The immense, unpredictable energy of an earthquake must go somewhere, and ancient engineers seem to have understood that it was far better to guide that energy than to futilely try to resist it outright. By intentionally creating controlled failure points, specific joints, walls, or sections built with slightly different materials or techniques, they could effectively program how a building would behave under extreme stress. These sacrificial elements were designed to fail first, absorbing and dissipating the seismic energy in a predictable manner. Think of it like a carefully designed fuse in an electrical circuit. It's the weakest point, chosen specifically to burn out and break the circuit, thereby saving the entire appliance from being fried. In architectural terms, a non-critical wall might be designed to crumble, or a series of columns might be meant to buckle in a specific sequence, channeling the destructive forces away from the most vital, load-bearing cores or sacred inner chambers of a temple. This strategic sacrifice preserved the overall integrity of the structure, preventing a total pancake collapse that would leave nothing but a heap of indistinguishable rubble. The goal wasn't to prevent any damage, but to ensure the damage that did occur was manageable, localized, and most importantly, non-fatal to the building's primary purpose. This principle finds a stunning parallel in some of the most advanced seismic engineering of our own time. Modern skyscrapers in earthquake zones often use systems like base isolation, where the entire building rests on flexible bearings that allow it to sway independently of the ground's shaking, or they incorporate dampeners that absorb vibrational energy. Even more directly comparable is the concept of a sacrificial beam or a fuse, where a specific, replaceable structural component is engineered to deform and fail first, protecting the rest of the building. The realization that ancient builders may have been employing a rudimentary yet profoundly effective version of this same principle centuries ago is a humbling testament to their observational genius. They may not have had the mathematical formulas of modern physics, but through centuries of trial, observation, and passed-down experience, they developed an intuitive, practical mastery of how forces move through stone and mortar. They learned the language of stress and strain written in cracked walls and toppled buildings, and they learned to speak back to it by designing structures that could answer a quake's violent shake with a controlled, life-preserving sigh. Beyond the cosmic and the practical, these architectural choices also served a master of immense power in the ancient world, politics. A new ruler ascending to power faced a monumental challenge: how to visibly establish a new era, to break from the previous regime and cement their own legacy in the minds of their people. What better way to demonstrate absolute authority than to command the very stones of your predecessor's greatest achievements? The ability to trigger a planned collapse transformed architecture into the ultimate prop in a drama of political theater. A new pharaoh, emperor, or king could orchestrate the ceremonial toppling of a specific wing of a palace, the closing of a grand gateway, or the ritual killing of a tomb's entrance. This was not random vandalism. It was a calculated, symbolic act of regicide against the old order, using buildings as a stand-in for the former ruler themselves. The collapse point became a powerful mechanism for this controlled erasure. The dramatic, thunderous fall of stone served as a visceral, unforgettable spectacle for the populace, a clear signal that the old way was literally being dismantled. Yet, this act of destruction was almost always followed immediately by an act of creation. The same workforce that carefully demolished a section would then rebuild it, often larger and more ornate, but directly atop the foundations of the old. This practice was politically brilliant. It conserved enormous resources. Why quarry entirely new stones when you can reuse the materials from the symbolically vanquished past? More importantly, it created a powerful narrative of continuity through transformation. The new ruler wasn't just destroying, they were improving, building upon the past to create a greater future, all while physically connecting their new dynasty to the sacredness and history of the site itself. We see echoes of this across cultures. In ancient Egypt, pharaohs frequently appropriated the monuments of their predecessors, recarving inscriptions and statues to feature their own likeness, effectively collapsing the previous ruler's identity and rebuilding their own in its place. In the Roman Empire, the practice of damnatio memoriae, the condemnation of a predecessor's memory, often saw their architectural commissions modified or dismantled. The intentional weak point in the architecture gave a new leader the power to perform this political reset on a grand public scale, turning the immutable landscape of stone into a malleable tool of statecraft and ensuring their name, and theirs alone, would be remembered by the stones that remained. Nowhere is this philosophy of intentional design more perfectly captured than in the very heart of the Great Pyramid of Giza. High above the fabled king's chamber, hidden from view, lies one of archaeology's greatest enigmas, a series of 5 compartments, now known as the relieving chambers. For centuries, their purpose was a complete mystery, seen by many as merely a clever solution to a structural problem, a way to divert the incredible weight of the masonry above away from the chamber's flat ceiling below. But this conventional explanation only scratches the surface of a far more brilliant and nuanced piece of engineering. The construction of these chambers is anything but random. They are built with immense precision-cut granite beams, some weighing over 50 tons each, stacked with deliberate gaps and empty spaces between them. This intricate arrangement creates a complex series of voids and stress points directly above the most important room in the entire pyramid. Rather than simply creating a stronger, more solid mass to bear the load, the builders went to extraordinary lengths to create a sophisticated system of distributed weight and potential failure zones. Some leading engineers and archaeologists now propose a radical reinterpretation. They suggest these chambers were not just built to hold weight up, but to manage how the entire structure would come down under extreme duress. In the event of a powerful earthquake or over the millennia of gradual settling, the specific arrangement of these massive granite beams and the empty spaces around them would have acted like a sophisticated shock absorber. The theory posits that the beams were designed to flex, shift, and even fracture in a precise, controlled sequence, instead of the entire ceiling of the king's chamber collapsing catastrophically in one sudden, crushing failure. The energy of the shift would be channeled upwards, absorbed and dissipated through these specially designed compartments. The relieving chambers would, in essence, sacrifice themselves in a planned and orderly manner, protecting the integrity of the sacred space below. It's a concept that turns our understanding of the pyramid's interior on its head. What appears to be a series of construction layers might actually be an ancient blueprint for controlled structural failure. The empty spaces aren't just gaps, they are expansion joints. The massive beams aren't just supports, they are programmable fuses. This wasn't a simple feat of brute strength. It was an act of predictive genius, demonstrating a profound understanding of material behavior under stress that we would only formalize with advanced mathematics thousands of years later. The Great Pyramid, often held up as the ultimate symbol of eternal, unchanging permanence, may in fact contain within its core a masterclass in planning for its own transformation and managed decay, proving that the ancient builders thought not in terms of forever, but in terms of how forever would eventually behave. This practice of architectural renewal reaches one of its most sophisticated expressions in the temples of the ancient Maya. At sites like Tikal in Guatemala or the magnificent complex of Palenque, we find not just one temple, but a series of them, each layer encapsulating the one before like the rings of a great stone tree. The process of building over an existing temple was far more than mere expansion. It was a carefully choreographed ritual of death and rebirth, and engineered collapse points were the critical mechanism that made it possible. Before a new layer of construction could begin, the old temple had to be properly decommissioned. This wasn't an act of disrespect, but one of profound sacred necessity. Specific elements of the existing structure were targeted for deliberate, controlled failure. Builders, who are also likely priests with deep ritual knowledge, would identify key architectural features: a grand doorway, a narrow corridor leading to an inner sanctum, or the vault of a particularly important chamber. Using their expert understanding of load and stress, they would methodically weaken these points. This might involve carefully removing a critical lintel stone, slightly undermining a foundational support, or even using fire in a controlled manner to thermally shock and crack specific stones. The goal was to trigger an inward collapse of these targeted areas, effectively creating a deliberate barrier of rubble that sealed off the heart of the old temple. From a purely practical standpoint, this served an essential engineering purpose. The resulting pile of debris created a stable, compact, and well-drained fill material upon which to build the new, larger pyramid. It was a brilliant form of recycling, turning the old sacred structure into the strong foundation for the new one, but the spiritual significance ran even deeper. This act of controlled demolition was a ritual killing. The old temple, having served its purpose in a completed cosmic cycle, had to be symbolically put to death to make way for its reincarnation in a new form. The thunderous collapse of the designated passages was the final breath of the old era. The rubble barrier wasn't just physical fill, it was a metaphysical seal, preventing the old spiritual energy from interfering with the new while simultaneously preserving it, entombed and protected for eternity. This practice created incredible time capsules for modern archaeologists. By tunneling carefully into these packed fills, researchers can literally walk back through time, uncovering perfectly preserved facades, murals, and offerings from temples that were intentionally buried for centuries. Each collapse point marks a moment of deliberate transformation, a planned pause in the life of a sacred site. It reveals a civilization that saw its architecture not as permanent and static, but as a living, breathing entity that required periodic renewal, with intentional destruction being the necessary and sacred first step in the cycle of creation. While the Maya and Egyptians often wove spiritual meaning into their structural choices, the Romans approached the problem with a characteristically pragmatic and systematic brilliance. Their empire was built on infrastructure aqueducts, roads, amphitheaters, and basilicas that needed to not only impress but endure and, crucially, be maintainable across vast distances and centuries. This practical necessity gave birth to an engineering philosophy that embraced planned failure as a feature of long-term management. Roman builders were master material scientists, and they applied this knowledge to create controlled weak points. They might use a slightly different mortar mix in certain joints, one with more sand and less lime, making it intentionally weaker and more brittle. To the untrained eye, every joint looked identical, but the engineer knew that under immense stress, these designated joints would crack first. This wasn't a sign of poor workmanship. It was a built-in circuit breaker for the building's structural load. The failure would happen in a predictable location, making diagnosis and repair straightforward for future engineers who might not have the original blueprints. Instead of a catastrophic, unpredictable collapse that could take down half a building, you'd get a controlled, localized failure that could be patched, repointed, or rebuilt, effectively extending the structure's life for another 100 years. This thinking reveals a profound humility and foresight. The Romans didn't assume their creations were perfect or eternal. They assumed that someday someone would need to fix them, and they had the generosity and wisdom to make that job easier. They were effectively leaving a maintenance manual written not in words, but in the very fabric of their buildings. The crown jewel of Roman architecture, the Pantheon in Rome, stands as the ultimate testament to this philosophy. Its massive, unreinforced concrete dome, still the largest of its kind in the world after nearly 2,000 years, is a masterpiece of material gradation and planned behavior. The engineers didn't use a single concrete recipe throughout. As the dome rises and the structural forces change, the aggregate, the stone mixed into the concrete, intentionally changes too. At the heavy, thick base, they used dense, solid travertine stone. But as the dome curves inward and upward, the aggregate gradually shifts to lighter and lighter materials, including porous pumice and even empty clay pots at the very top around the oculus. This was a deliberate and calculated move. The designers understood that in the worst-case scenario, if the immense dome were ever to fail, they needed to control how it would fail. By making the top significantly lighter than the base, they ensured that any potential collapse would most likely occur inward, toward the center of the building. The heavy, strong base would act as a containment ring, holding the majority of the structure in place while the lighter top sections crumbled into the open space below. This would minimize collateral damage to the surrounding structure, the attached portico, and the city outside. It's a breathtaking piece of risk management engineered directly into the materials. They weren't just building for the dedication day, they were planning for a potential disaster a millennium in the future, designing a failure that would be a contained event rather than a city block-leveling catastrophe. This level of forethought is almost unimaginable today, yet it is a key reason why the Pantheon has survived earthquakes, invasions, and the sheer weight of time when so many other contemporary structures have vanished. It wasn't built to be invincible, It was built to be resilient and repairable, a distinction that has made all the difference. So how do we know the difference? How can archaeologists confidently point to a pile of ancient rubble and declare it not a tragedy, but a feature? It all comes down to a meticulous forensic science, a form of architectural detective work that looks for the unmistakable fingerprints of intent. The first and most obvious clue is pattern. Nature is chaotic, human design is not. Accidental collapse from an earthquake or simple decay creates random, chaotic fracture lines and piles of debris of all sizes. But an intentionally engineered failure point leaves a very specific signature. Archaeologists look for symmetrical, repeating patterns of cracking that couldn't possibly occur by chance. Imagine finding a series of columns where every third one has shattered in an identical way, or a wall that has collapsed inward along a perfectly straight, vertical line, as if it were a pre-cut seam. That isn't the work of random chaos, it's the result of a calculated design. The materials themselves tell another part of the story. Ancient builders were masters of their craft, and their choice of stone or mortar was never accidental. When we find that a single, critical lintel stone over a major doorway is made of a softer, more brittle sandstone, while every other lintel in the structure is made of hard granite, that's a red flag. Why use a weaker material at the most critical stress point unless you want that point to fail under a specific amount of pressure? Similarly, the mortar mix might be deliberately different, more sandy and less sticky, in the joints of one specific arch, ensuring it would be the first to give way. The construction techniques offer further proof. We might find that stones in a particular section were laid with unusual gaps behind them, creating voids that would concentrate stress, or that they were placed with their natural grain oriented in the direction of easiest fracture. These aren't oversights, they are sophisticated applications of stone-working knowledge. The most compelling evidence, however, often comes from what is found at these failure points. The discovery of ritual artifacts is a game changer. If excavators find a cache of ceremonial objects, an offering of precious jewels, or the remains of a sacred animal deliberately placed right at the base of a collapsed pillar, the context becomes undeniable. That pillar wasn't knocked over in a raid or a quake. It was pulled down in a ceremony, with the offering left as a spiritual payment or a mark of significance. This combination of physical and contextual evidence allows experts to separate misfortune from design. It transforms a scene of destruction into a readable blueprint, revealing where ancient engineers wrote their instructions for controlled transformation directly into the stone, waiting centuries for us to learn how to read their language. This mastery over materials reveals a fascinating truth about ancient engineering. It was a science of applied experience rather than theoretical calculation. Without the formal physics equations we rely on today, these builders developed an intuitive, almost instinctual understanding of how different stones would behave under stress over centuries. They learned through generations of observation which sandstone would crumble predictably, which granite would fracture along clean lines, and which limestone could absorb immense pressure before shattering. This knowledge was then applied with surgical precision. In a single structure, you might find half a dozen different mortar recipes, each mixed for a specific purpose. Primary load-bearing walls would be bound with a mortar of incredible strength, using crushed brick, lime, and sometimes even volcanic ash to create a cement-like bond that rivaled the stone itself. But then, at a single strategic joint, perhaps where a lintel met a supporting pillar, the recipe would change. Here, the mix might include more sand, less binder, or even organic materials like straw that would decay over time, deliberately creating a weaker point. The builders weren't just making mortar, they were programming a timeline of failure into the building's very joints. This selective use of materials extended to the stones themselves. The orientation of sedimentary rocks is a perfect example. A block of sandstone or limestone has a natural grain, much like wood. Placed with its grain running vertically, it can bear tremendous compressive weight. But if that same block is turned on its side with the grain running horizontally, it becomes far more susceptible to shearing forces and will split much more easily along its natural layers. Ancient engineers used this property to their advantage. In a vast wall, almost every stone would be placed for maximum strength, but in one critical location, a single keystone or a series of blocks might be intentionally oriented with their grain horizontal, creating a predetermined fracture plane. Under enough stress, the wall wouldn't collapse randomly. It would crack along this engineered weakness, guiding the failure in a specific and controlled direction. Beyond composition and orientation, they also engineered weakness through geometry. The creation of intentional voids is one of the most clever techniques. A small, carefully shaped empty space left behind a crucial stone or a channel carved through what appears to be a solid mass doesn't just reduce weight. It acts as a stress concentrator, a focal point where forces will naturally gather and intensify. It's the architectural equivalent of a perforated tear line on a piece of paper. When the building experiences a threshold level of strain, the failure isn't random. It originates from this designed void and propagates outward exactly as intended. This approach required a holistic view of the structure as a dynamic system, not a static monument. They understood that a building breathes, settles, and responds to its environment. Their goal wasn't to create an indestructible object, but to create a predictable one, a structure whose behavior over centuries could be foreseen and guided by the hands of its original creators. This materials-level engineering represents a profound dialogue between human intention and physical reality, a conversation written in stone and mortar that we are only now beginning to fully decipher. This incredible diversity in engineering philosophy means that if we could travel back in time and ask a master builder from Egypt, Mesoamerica, Rome, and Greece about their approach to structural weakness, we would get 4 completely different answers, each perfectly logical within their own world. Their choices were not random. They were direct reflections of their deepest cultural priorities, their environment, and their relationship with time itself. The Egyptian architect working under the burning sun along the Nile was consumed with the concept of eternity. For them, a tomb or a temple was a machine for the afterlife, a permanent vessel designed to last for millions of years, or jet as they called it. Their ideal was absolute, unchanging permanence. This doesn't mean they were ignorant of structural stresses, quite the opposite. Their solution was to over-engineer to an almost unimaginable degree, using megalithic stones, perfect fits, and a sheer mass so colossal that the concept of a planned failure point seems almost blasphemous. Yet, even here, we find a form of intentional stress management. The Great Pyramid's relieving chambers are the ultimate example, not a weakness in the traditional sense, but a sophisticated internal system designed to manage failure, to channel immense forces in a specific, non-destructive way. The Egyptian approach to collapse was to preempt it entirely through overwhelming strength and brilliant internal redistribution, ensuring the exterior shell remained pristine and eternal, a perfect monument for a god-king's eternal soul. Their intentional weakness was hidden deep within, a secret safeguard against the millennia, all in service of creating an outward appearance of perfect, unchanging solidity. Cross the ocean and step into the humid rainforests of the Maya world, and you enter a universe governed by an entirely different rhythm. Here, time was not a linear march toward eternity, but a great spinning wheel of cycles, the cycles of the seasons, the cycles of the Venus calendar, the cycles of life, death, and rebirth. Their architecture had to reflect this cosmic truth. A temple was not meant to stand frozen forever. It was meant to live, die, and be reborn, just like the maze that sustained them or the rulers they deified. This is why they so wholeheartedly embraced cyclical rebuilding. Their intentional collapse points were not hidden but were central to the ritual process. A specific doorway would be carefully weakened so that during a ceremony marking the end of a major calendar cycle, it could be ceremonially broken through or collapsed, symbolizing the death of the old era. This controlled demolition was the necessary first step in building a new, larger temple layer directly over the old one. The rubble from the collapse wasn't waste, it was sacred fill, the literal body of the old temple becoming the foundation for the new. This approach was profoundly sustainable, recycling materials and labor, but its primary driver was spiritual. It physically connected each generation to the past while allowing for growth and change, creating a living timeline of stone where you could literally see the layers of history. The Maya built knowing their work would be entombed, and they saw that not as a failure but as the fulfillment of its sacred purpose. Meanwhile, in the sprawling, pragmatic Roman Empire, the problem was one of scale and administration. How do you maintain colossal aqueducts, vast amphitheaters, and massive bath complexes across 3 continents for centuries with limited communication? The Roman answer was standardized, maintainable engineering. Their genius lay in anticipating future problems and baking the solutions into the original construction. A planned weak point in a Roman structure was less about ritual and more about practical repair. They might use a slightly inferior mortar mix in a specific series of joints in an aqueduct's arch. When the inevitable ground settlement occurred decades later, the stress would concentrate at those predetermined points, causing a clean, localized crack rather than a catastrophic shatter of the entire arch. A maintenance crew from 200 years in the future would arrive, see the precise location of the failure, and know exactly how to fix it. The Romans engineered for the long term by planning for manageable, localized decay. Pantheon's dome is the masterpiece of this philosophy. Its changing composition, lighter at the top, ensures that in a worst-case collapse, the failure would be inward and contained, minimizing damage to the surrounding city. This wasn't just building, it was institutional empathy, a profound consideration for the engineers and citizens of the future, ensuring the empire's heart would keep beating with minimal disruption. The Greeks, in their pursuit of ideal beauty and mathematical perfection, took yet another path. For them, the aesthetics of a structure, its proportion, its harmony, its visual flow were paramount. A planned weakness that was visible would have been an anathema. Their solution was to achieve such a perfect balance of form and function that the need for obvious failure points was eliminated. The Parthenon's subtle curves, its slight inward lean of columns, and its refined optical corrections are all examples of this. These weren't weaknesses but incredibly sophisticated reinforcements against visual distortion and seismic activity, distributing stress so evenly that the structure became resilient through its perfection. Any intentional yielding was so seamlessly integrated into the overall design that it became invisible, a testament to their belief that true strength arose from perfect balance, not from obvious sacrificial elements. Each civilization, therefore, speaks to us through its stones. The Egyptians whisper of eternity, the Maya chant of cycles, the Romans dictate a maintenance manual, and the Greeks sing of perfect harmony. Their collapse points, whether hidden, ritualized, practical, or invisible, are their signatures, revealing how they saw their place in time and the legacy they hoped to build. It's a fascinating thought that the most advanced demolition experts of today might share a common playbook with engineers who worked thousands of years ago. When a modern crew brings down a skyscraper in a dense urban area, they don't just hope it falls in the right direction. They undertake months of meticulous planning, using computer models to identify critical support points. Then, they strategically place precisely measured explosives to remove those supports in a carefully timed sequence. The goal is to make the building collapse in on itself, a process known as implosion, minimizing damage to the surrounding structures and ensuring public safety. This entire practice hinges on one core principle: the deliberate and calculated introduction of weakness to control chaos. The ancient builders, in their own way, were masters of this very same art. They may not have had nitroglycerin or electronic detonators, but they possessed an intimate, almost intuitive understanding of structural behavior. Their tools were different variations in mortar strength, the strategic orientation of stone grains, the intentional creation of hidden voids, but their objective was strikingly similar. They designed their structures with a specific failure mode in mind, programming the path of collapse long before the trigger was ever pulled. This shared philosophy reveals a profound truth about engineering itself. The fundamental laws of physics, gravity, load paths, and stress distribution are eternal. Whether you're working with 21st century steel or 25th century BCE limestone, these forces behave in predictable ways. Ancient engineers, through centuries of observation and passed-down experience, learned to speak the language of these forces fluently. They understood that a structure doesn't fail randomly, it fails along the path of least resistance. So, by carefully engineering what that path would be, they could dictate the story of the collapse. A modern demolition expert uses explosives to create a sequential failure of a building's steel frame, guiding it downward. An ancient engineer might have designed a temple with a series of columns where every third one was slightly weaker, knowing that in an earthquake, those columns would buckle first, causing the roof to sag in a specific section and protecting the inner sanctum. In both cases, the designer is not preventing failure but choreographing it, turning a potentially catastrophic event into a controlled and predictable outcome. The parallels extend even to the concept of a sacrificial element. In modern engineering, this is a component designed to fail first in order to protect the rest of the system. Think of an electrical fuse that blows to save an appliance or a crumple zone in a car that deforms to absorb impact and protect the passenger cabin. Ancient structures are filled with these sacrificial elements. A single lintel stone made of softer material above a doorway was a fuse. A wall built with a more brittle mortar mix was a crumple zone. These elements were meant to be the first to give way, absorbing destructive energy and channeling it away from more critical, irreplaceable parts of the structure, like a painted burial chamber or a vault holding sacred relics. This approach demonstrates a holistic systems thinking that we often assume is a modern invention. They weren't just building walls, they were designing an interactive system that would respond to environmental stresses in a pre-programmed way, sacrificing the expendable to save the essential. Perhaps the most humbling aspect of this comparison is the realization that modern technology doesn't always invent new principles. It often just rediscovers ancient ones with more powerful tools. The use of computer simulations to model collapse patterns is a technological leap, but the underlying principle of progressive collapse and load redistribution was clearly understood and applied millennia ago. It suggests that there are multiple paths to sophistication. One path is through advanced mathematics and material science, which is our modern way. The other path is through deep, accumulated experiential knowledge refined over generations, the way of the ancient master builder. This doesn't diminish our accomplishments, but instead adds a layer of respect for theirs. It connects us across time, showing that the human drive to understand and harness the physical world, to impose order on chaos is a constant thread running through history. The methods change, but the fundamental intelligence behind them echoes through the ages, from the quarries of Egypt to the controlled demolition sites of our modern cities. This profound spiritual dimension reveals that for many ancient cultures, architecture was far more than shelter or monument. It was a living participant in the cosmic order, a vessel for communication with the divine that required its own cycle of life, death, and rebirth. The practice of building with intentional collapse points transforms these structures from inert stone into something almost animate, an entity capable of making the ultimate sacrifice on behalf of the community. This concept of sacrificial architecture turns our modern understanding of value completely on its head. Why pour generations of labor and vast resources into a building designed to be partially destroyed? Because its value wasn't measured solely in its physical permanence, but in its spiritual utility. The act of creation contained within it the seed of its own destruction as the highest form of offering. We see this powerful idea manifested across different civilizations. In ancient Mesopotamia, the practice of ritual entombment of temples involved carefully sealing off doorways and sometimes triggering controlled collapses within sacred precincts when dedicating a new structure atop an old one. This wasn't abandonment, it was a sacred offering of the entire building to the gods, preserving its spiritual energy while making way for renewal. Similarly, in certain Andean cultures, evidence suggests that parts of ritual complexes were designed to be dismantled or collapsed during ceremonies that reenacted creation myths, where chaos must precede cosmic order. The destruction of a specific wall or platform became a participatory act in the maintenance of the universe itself. The architectural weakness was therefore not a flaw but a sacred interface, a designated point where the human world could interact with the divine through a controlled act of dissolution. This perspective helps resolve what seems like a paradoxical investment of resources. A society wouldn't meticulously design a weakness into their most important building unless that weakness served a purpose even more valuable than structural integrity. That greater purpose was spiritual security and cosmic balance. The ability to ritually sacrifice a part of the structure, to literally bring a piece of the built environment down as an offering, was a demonstration of piety on a monumental scale. It acknowledged a fundamental truth these cultures understood deeply, that all human creation is ultimately impermanent before the eternal divine. By designing for their own destruction, they were humbly admitting this truth into the very heart of their greatest achievements. The collapse point became a permanent reminder of human limitation and the supremacy of the gods, etched into stone for all to see. It was an act of devotion written in the language of engineering, ensuring that even their most proud accomplishments contained a built-in mechanism for humility. But this architectural foresight extended far beyond the immediate need for defense. It blossomed into one of antiquity's most profound and forward-thinking concepts, the creation of intentional time capsules. Imagine a civilization so invested in its legacy that it engineers its greatest buildings not just for the present, but as messages in a bottle, sealed for an audience millennia in the future. This was the genius of using collapse points for preservation through controlled access. Ancient builders transformed structural vulnerability into the ultimate security system, designing specific triggers that would seal away sacred knowledge, precious artifacts, or entire ritual chambers until precisely the right moment. It was a way of speaking directly across the centuries, ensuring that their most valued treasures would survive wars, cultural shifts, and the slow decay of time, waiting for a future generation deemed worthy of rediscovery. The mechanism itself was often breathtakingly simple yet required deep architectural insight. A massive stone door might not be hinged at all, but instead perfectly balanced on a pivot point deep within the wall. The knowledge of how to open it, a specific stone to push, a hidden lever to pull, would be passed down through a secret priestly lineage. If that knowledge was ever lost, or if an intruder tried to force their way in, the act of tampering would trigger the collapse mechanism. A key lintel stone would drop, a counterweight would be released, and tons of rubble would funnel down a predetermined shaft, permanently entombing the passageway. This wasn't a panic-induced cave-in. It was a pre-programmed response, a dead man's switch built into the very fabric of the building. The goal wasn't just to hide something, but to protect its sanctity by making it utterly inaccessible to anyone without the precise cultural key. We see evidence of this in places like the labyrinthine tombs in Egypt's Valley of the Kings, where deep burial chambers were sometimes found with corridors deliberately packed from floor to ceiling with stone debris. Initially, archaeologists assumed these were the results of flash floods or later collapses, but the patterns tell a different story. The rubble is often too neatly stacked, the blocking too complete and systematic to be an accident. It appears to be the result of a designed failure, a ritual sealing performed by the last priests to leave the tomb, ensuring that the pharaoh's journey to the afterlife would remain undisturbed. Similarly, in Mycenaean Greece, the magnificent beehive tombs known as tholoi were often entered through a towering doorway capped by a single, immense lintel stone weighing tens of tons. The entire stability of the door's structure depended on that one critical stone. Remove it, and the facade above could catastrophically collapse. This lintel was the ultimate safeguard. It made the tomb virtually impervious to casual looting, as any attempt to break in around it risked bringing the entire entrance down. The knowledge of how to properly support the structure during entry was likely a closely guarded secret, turning a seemingly simple architectural feature into a sophisticated lock. This long-term thinking is perhaps the most staggering aspect. These builders were not just concealing things from their contemporaries, they were planning for a distant, unknown future. They created these sealed chambers with the full expectation that they would remain closed for centuries, if not forever, preserving a snapshot of their culture in perfect stillness. The controlled collapse mechanism was the guarantee of that promise. It ensured that the contents wouldn't be slowly picked over by generations of minor looters, but would remain pristine, waiting for a moment of rediscovery that the original builders would never see. In this light, the collapse point transcends its physical form. It becomes a covenant with time itself, a deliberate act of cultural memory that uses planned structural failure not as an end, but as a courageous and hopeful beginning for a story they knew would be finished by others. Beyond the realms of ritual and defense, these architectural strategies reveal a remarkably pragmatic and sustainable approach to managing some of the ancient world's most precious commodities, building materials and human labor. The sheer scale of quarrying, transporting, and dressing stone for a single major temple was a generational undertaking, consuming vast economic resources and communal effort. In this context, the idea of simply abandoning an old structure to the elements and starting from scratch elsewhere wasn't just spiritually dissonant, it was economically reckless. This is where the genius of designed collapse points as a tool for resource management truly shines. A community could plan for the eventual renewal of a sacred site, not as a total loss, but as an opportunity for harvesting. By engineering specific failure points, they created a controlled method for deconstruction. Instead of painstakingly prying apart perfectly fitted stones and risking damage, they could trigger a precise collapse that would bring down a targeted section, like a non-load-bearing wall or a decorative facade, in a way that produced reusable blocks. The resulting rubble wasn't seen as waste, It was a quarry in place, a carefully generated stockpile of pre-cut, spiritually significant stone, ready to be integrated into the next phase of construction. This practice of architectural recycling turns our modern concept of waste on its head. We tend to build with an assumption of permanence, and when a building outlives its use, demolition creates a massive waste stream. The ancient approach, by contrast, viewed buildings as temporary repositories of value, with their materials always holding the potential for future use. The collapse point was the mechanism that released that stored value back into the building cycle. This created a closed-loop system of astonishing efficiency. The stones from a temple dedicated to a grandfather's reign could be respectfully gathered and used to build a larger temple for his grandson, creating a physical lineage within the architecture itself. This wasn't seen as disrespectful to the past. Rather, it was a way of honoring it by weaving its substance directly into the future. The spiritual significance of the original materials was often preserved through this process. A stone that had been part of a sacred altar didn't lose its sanctity when it was moved. Its holiness was transferred, making the new structure instantly consecrated by the physical presence of the old. This approach also had profound implications for labor management. Large-scale construction projects could be planned in phases that aligned with a community's capacity. During a period of abundance, a string of good harvests, or a time of peace, a grand new phase could be initiated, using the harvested materials from the last cycle as a foundation. In leaner times, the community could still maintain the site through smaller rituals and repairs, preserving the knowledge and tradition until resources were available for the next great renewal. This cyclical pattern of build, collapse, harvest, and rebuild created a sustainable rhythm of architectural life that was deeply integrated with the economic and environmental realities of the time. It stands in stark contrast to our modern, often linear model of construction and demolition. Perhaps there is a powerful lesson embedded in these stones for our own era of resource scarcity and environmental concern. The ancient world mastered the art of building with humility and foresight, seeing value not just in new materials but in the intelligent and respectful reuse of the old, guided by an engineering wisdom that knew exactly how to take something apart with the same care used to put it together. This profound and potentially dangerous knowledge of how to make a mighty structure fail was not common currency. It was the closely guarded secret of elite builder guilds, master craftsmen, and often the priestly classes who understood the sacred geometry and ritual significance behind every stone. Think of them not just as architects, but as the keepers of a sacred technology, a living library of applied physics, material science, and spiritual doctrine, all encoded in architectural practice. Their power was immense. They held the keys to both creation and dissolution. They could raise a temple that would touch the sky, and they alone knew the precise ritual and technical sequence to bring a part of it down in a controlled, sacred manner when the cosmic calendar demanded it. This control over the life cycle of a community's most important buildings granted them unparalleled influence, placing them at the very heart of political, spiritual, and economic life. A ruler might command a pyramid to be built, but it was the master builder who knew how to make it truly eternal through its designed vulnerabilities. This culture of secrecy provides the crucial answer to a persistent question in archaeology. If this knowledge was so sophisticated, why don't we find detailed engineering texts or explicit blueprints explaining it? The answer is that this was tacit knowledge, passed down through apprenticeship and oral tradition, protected from the uninitiated. Writing it down would have been like giving away the crown jewels. The techniques were likely embedded in myths, songs, and ritual practices, disguised to the outsider but perfectly clear to the trained members of the guild. This is precisely why the evidence we find today is so subtle and requires such careful, interdisciplinary interpretation. We are not reading an instruction manual. We are piecing together a forgotten language by comparing the architectural fingerprints left at sites separated by oceans and centuries. A specific pattern of stone orientation in a Maya temple corridor might find its echo in the mortar composition of a Roman aqueduct arch. The symmetrical collapse of a particular chamber in an Egyptian tomb might mirror the strategic placement of lighter materials in the Pantheon's dome. It is through this comparative forensic analysis that the patterns emerge, revealing a shared, deep understanding of structural behavior that was too valuable and too powerful to be written down for just anyone to see. The silence in the historical records isn't an absence of knowledge. It is the mark of its supreme value, a secret so potent it was meant to be felt in the stones, not read on a page. This incredible geographical diversity meant that a master builder in earthquake-shaken Anatolia would approach structural failure in a completely different way than his counterpart in the stable, humid lowlands of the Maya world. Their designs weren't just a matter of style, they were direct, brilliant adaptations to the specific challenges whispered by the very ground beneath their feet and the sky above their heads. In regions where the earth itself was untrustworthy, like along the seismic belts of the Mediterranean or the Andes, collapse points became a form of architectural judo. Here, the primary design goal was survival through strategic sacrifice. Engineers in these zones learned to read the landscape's tremors not as random acts of destruction, but as predictable forces that could be managed. They observed how different parts of a building failed during quakes and used that hard-won knowledge to program future responses. A temple in ancient Greece might be constructed with intentionally weaker mortar in certain non-critical walls. When the next tremor struck, these designated sections would crumble first, absorbing and dissipating the seismic energy like a controlled explosion, thereby channeling destructive forces away from the load-bearing columns of the inner sanctum. This wasn't a flaw, it was a sophisticated damping system, a way of letting the building sigh in relief at predetermined points to avoid a catastrophic scream of total collapse. The choice of materials was critical in these areas. Builders often selected stones that would fail in predictable, non-catastrophic ways. A sandstone block might be preferred over brittle granite for a specific lintel because it would deform and crack gradually under stress, giving audible warnings before failing completely, rather than shattering without notice. The very geology of the region became a partner in the design process, with local material properties dictating the most effective failure mechanisms. Conversely, in geologically stable regions like the Nile Valley or the plains of Mesopotamia, where earthquakes were rare but the passage of dynasties was not, the purpose of engineered weaknesses shifted dramatically. Here, the primary environmental forces were not physical but temporal and spiritual. The challenge wasn't surviving earth tremors, but managing the cycles of ritual time and political change. In the dry, stable air of Egypt, a block of limestone could sit for millennia without significant weathering. This permanence allowed engineers to design collapse points with incredible precision for very long-term ritual functions. A hidden corridor in a pyramid might be blocked by a single, perfectly balanced keystone. The knowledge of how to trigger its collapse could be passed down through priestly lineages, to be used centuries later during a sacred ceremony to seal the tomb for eternity. The arid climate ensured that the mechanism would remain functional, free from the rust or rot that would plague it in a wetter environment. The environmental stability allowed for a different kind of engineering foresight, one that planned for a specific, human-triggered event in the distant future, relying on the unchanging nature of the stone and the climate to preserve the mechanism's integrity. Climate itself was a relentless co-designer. In the humid, rain-drenched jungles of Central America, the Maya battled constant moisture and aggressive vegetation. Their mortar, made from burned limestone, was highly effective but could be weakened by persistent water infiltration. A clever engineer might use this to their advantage. They could design a roof section where water would be channeled to a specific joint, knowing that over a 50-year cycle, the mortar there would degrade predictably faster than elsewhere. This created a natural, time-release collapse point that could be anticipated and incorporated into the ritual calendar for the temple's renewal. In the frigid north, like in parts of ancient Scotland, the freeze-thaw cycle was the dominant force. Builders of blocks and stone towers would intentionally leave small cracks or use specific stone types that absorbed water. When the water froze and expanded, it would slowly, over generations, widen these cracks along predetermined lines. This wasn't poor construction. It was a way of ensuring that when the structure eventually needed to be decommissioned or rebuilt, it would fail along those engineered seams, making the process of harvesting reusable stone much safer and more efficient. The local availability of materials ultimately dictated the palette of possible failures. A civilization with access to abundant clay might design collapse points using baked bricks that could be easily dismantled. A culture working only with immense granite megaliths, however, had to think on a grander scale, designing weaknesses through precise geometry and balance rather than material frailty. This beautiful adaptation to local conditions means there is no single, universal ancient secret to collapse points. Instead, there is a brilliant global tapestry of solutions, each thread perfectly woven to answer the unique demands of its environment, proving that ancient genius was not a monolith, but a chorus of diverse voices, each singing the same song of resilience in their own local key. This deep integration of mathematics transforms what might look like random cracks or oddly placed joints into something far more profound, the physical manifestation of a calculated equation. Ancient builders didn't just build, they computed with stone. Their blueprints were woven from sacred geometry, the golden ratio pi, the precise proportions found in nature, and these same governing principles dictated not only a structure's form but also its carefully planned points of failure. A weak point was never an afterthought. Its location was determined by the same harmonic logic that decided the height of a column or the curve of an arch. It was placed at a specific harmonic node, a point of geometric significance within the overall design, ensuring that any failure would propagate through the building in a predictable, mathematically ordained pattern. This approach reveals an engineering mindset of breathtaking foresight. By anchoring a collapse point to an immutable mathematical constant, the builders could anticipate its behavior not just for years but for millennia. They understood that physical forces, whether the slow creep of settling, the sudden shock of an earthquake, or the deliberate pull of a ritual trigger, would always respect the laws of physics, which are themselves written in the language of mathematics. A lintel designed to fracture under a specific load would do so whether it was in 10 years or 10 centuries, because the relationship between stress, material strength, and geometric form is a constant. This allowed them to effectively program their structures, creating architectural algorithms where a specific input, a tremor of a certain magnitude, or the removal of a key stone, would reliably produce a predetermined output, a controlled, localized collapse that preserved the whole. Perhaps the most fascinating aspect is how this mathematical foundation bridges the gap between the tangible and the transcendental. For these cultures, numbers and geometry were not abstract concepts. They were the fundamental building blocks of the cosmos, the language of the gods. A ratio like the golden section was seen as a divine proportion, a pattern echoing through the growth of shells, the spacing of planets, and the ideal human form. By designing a temple according to these principles, they were aligning it with the universal order, and by extension, the planned collapse points within that temple also participated in this sacred order. The failure of a specific wall wasn't just a physical event, it was a cosmological one, a moment where the building's mathematical destiny was fulfilled. This meant that the act of demolition could be a sacred act, a ritual that resonated with the very mathematics of creation. We can see this principle at work in countless ancient sites. The precise dimensions of the king's chamber in the Great Pyramid are a famous example, reflecting a sophisticated understanding of pi and the Pythagorean theorem. The relieving chambers above it, which we now suspect were designed to manage failure, are integral to that mathematical scheme. Their placement and proportions are not random, but are calculated components of the pyramid's internal stress diffusion system. Similarly, the Parthenon in Athens is renowned for its optical refinements, subtle curves, and inclinations that correct for visual distortion, all based on complex geometric relationships. Every element, down to the smallest detail of its construction, was part of a unified mathematical whole. It stands to reason that any planned yielding within such a structure would also conform to this overall geometric integrity, ensuring that even in failure, the building's sacred proportions were honored and its core identity preserved. This seamless fusion of math, material, and meaning created an architecture that was not merely strong but intelligent, a built environment that could think ahead, collaborate with natural forces, and even orchestrate its own graceful transformation according to a divine and eternal plan. Perhaps the most beautiful aspect of these engineered transformations was the way they wove the entire community into the fabric of their own sacred spaces. This wasn't work reserved for a secretive class of priests and master builders alone. The cyclical process of collapse and renewal became a powerful engine for social cohesion, a shared project that defined a community's identity across the generations. Imagine the scene in a Maya city-state as a great calendar cycle drew to a close. The entire population, from the highest noble to the most humble farmer, would have a role to play. The act of ceremonially collapsing a specific part of the old temple wasn't a somber affair of destruction, but likely a vibrant, noisy, and deeply participatory community festival. Teams might be organized to pull on ropes attached to strategically weakened pillars, while others chanted and drummed, turning the thunderous crash of falling stone into a collective, celebratory act of cosmic renewal. This shared labor created a powerful sense of common purpose. The back-breaking work of hauling the resulting rubble to form the new temple's core, followed by the careful placement of new stones, was more than just construction. It was a physical ritual that bound everyone together. In an era without modern machinery, the sheer manpower required for these projects meant that everyone's contribution was essential. This process transformed architecture from something built for the people into something built by the people, creating an indelible emotional investment in the final structure. A father could point to a specific stone he had set with his own hands, and his son, decades later, would help carefully deconstruct that very same section to make way for his own contribution. This created a living, physical lineage, a conversation in stone between generations that reinforced cultural continuity and shared identity in the most tangible way possible. Crucially, these rebuilding cycles served as a massive, open-air classroom for the transmission of incredibly sophisticated knowledge. The master builders and architects didn't just issue orders, they used the process as a hands-on apprenticeship. A young initiate wouldn't just learn how to cut a stone by reading a manual. They would first participate in the careful, observational process of unbuilding. They would see exactly how their predecessors had oriented certain blocks to create a planned weakness, or how a specific mortar mix had performed over a 50-year cycle. This deconstruction phase was an invaluable education in cause and effect, revealing the long-term consequences of architectural decisions in a way that's almost impossible to learn from new construction alone. By taking apart the work of the previous masters, the next generation internalized the principles of engineering, the properties of materials, and the sacred geometries that governed their craft. This ensured that vital technical knowledge wasn't just preserved in abstract theory, but was passed down through lived, physical experience. The collapse point itself became the ultimate teacher, demonstrating the precise mechanics of failure and the profound wisdom in designing for it. This created an unbroken chain of expertise, where each generation could stand on the shoulders of the previous ones, refining techniques and adding their own innovations, all while maintaining a deep reverence for the foundational knowledge embedded in the stones of their ancestors. The structure itself, in its endless cycle of death and rebirth, was the greatest textbook they would ever know. This deep connection to mythology meant that for many ancient peoples, a building was never just a building. It was a living story, a three-dimensional stage where the great cosmic dramas of their belief systems could be physically enacted and experienced. The very stones were actors in this eternal play, and the planned collapse points were their carefully scripted exits and transformations. A temple wasn't merely a place to worship a god of earthquakes. It was designed to interact with that god's power in a symbolic dialogue, with specific walls or pillars engineered to fail in a way that mirrored the deity's mythological actions. This transforms our understanding of these sites from passive monuments into active participants in the spiritual life of a culture. We can see this principle vividly in the ancient Norse worldview, where the concept of Ragnarök, the great battle that would end the world and lead to its rebirth, was a central tenet of their cosmology. This wasn't a distant metaphor, it was a reality they believed would one day unfold. Their architecture, particularly their great mead halls, sometimes reflected this profound narrative. Certain structural elements, like a central pillar known as the stallari or supporting man, held immense symbolic weight. It was more than a post holding up a roof. It was the mythological tree Yggdrasil itself, the axis of the world. Some archaeologists theorize that these pillars might have been designed with a symbolic, if not literal, weakness. In the event of the hall's intentional decommissioning, perhaps after the death of a great chieftain, the ritualistic toppling of this central pillar would have been a breathtaking act of symbolic destruction. As the great beam fell, bringing a section of the roof down with it in a controlled collapse, it would have physically reenacted the fall of Yggdrasil and the coming of Ragnarök. This wasn't an act of despair, but one of profound faith and cyclical hope. The collapse was a necessary death that made way for the promised rebirth, turning a structural event into a powerful communal affirmation of their most sacred beliefs. Similarly, in the ancient Near East ziggurats, those massive stepped pyramids dedicated to the gods were seen as literal bridges between the earthly and divine realms. Their construction was itself a reenactment of the creation myth, with each level representing a stage in bringing order out of primordial chaos. The maintenance and periodic renewal of these structures were critical to maintaining cosmic order. If a specific ramp or terrace was designed to be ritually dismantled and rebuilt, that controlled demolition was far more than simple maintenance. It was a reenactment of the cosmic battle where the gods defeated chaos, a necessary ritual to prevent the world from sliding back into disorder. The act of breaking a specific sequence of bricks and then replacing them was a physical prayer, a way for the entire community to participate in holding the universe together. The architectural weakness was the designated point where human ritual action could interface with the divine plan, making the entire population custodians of cosmic stability. This practice was also a powerful tool for communicating incredibly complex theological and cosmological ideas to a population that was largely non-literate. You didn't need to be able to read sacred texts to understand the story being told by the stones. A pilgrim visiting a temple complex and witnessing a ceremony where a specific, famously weak lintel stone was finally replaced after decades of slow cracking would receive a visceral lesson in patience, decay, and renewal. The very design of the building itself became an illustrated book, its collapse points serving as dramatic punctuation marks in a story written in architecture. The repeated patterns we see across culturally connected sites, certain types of doorways always sealed, specific altar orientations always maintained, are not evidence of a lack of imagination, but rather a shared symbolic language. These architectural features were a universal code, instantly understandable to any initiate within that cultural sphere, transcending local dialects and specific tribal identities to create a unified spiritual landscape built from a common language of stone and intentional vulnerability. This profound embrace of contradiction lies at the very heart of the ancient builder's genius, the ability to hold two opposing ideas in perfect, functional balance. They constructed monuments intended to echo through the ages, yet they deliberately wove threads of fragility into their fabric. This wasn't a sign of uncertainty or flawed planning. It was a sophisticated philosophical stance made manifest in stone. They understood that true resilience isn't about defiantly resisting change, but about gracefully collaborating with it. By accepting that all things must eventually transform, they gained a measure of control over that very process, turning inevitable decay from a chaotic enemy into a managed, even sacred event. The collapse point, therefore, becomes more than a structural feature. It is a profound meditation on the nature of existence itself. It is a physical acknowledgement of a universal truth, that permanence and impermanence are not opposites, but partners in a continuous dance of creation and dissolution. This ancient wisdom stands in stark contrast to much of our modern architectural philosophy. We often build with an almost defiant ambition for absolute permanence, pouring concrete and steel in a bid to create something that will stand forever, unchanged and unchallenged by time. We fight against nature's forces with ever stronger materials and more rigid designs, viewing any crack, any sign of wear as a mark of failure. This pursuit of an impossible eternity can lead to a brittle kind of strength, where a structure holds firm until it doesn't, often resulting in catastrophic, unpredictable failure when its limits are finally exceeded. The ancient approach offers a radically different model, one of flexible endurance. By designing for a graceful, planned decline, they created structures that could absorb shocks, adapt to stresses, and transform over incredible timescales without completely losing their integrity or their purpose. This is the essence of the paradox. By accepting and planning for their own impermanence, these buildings achieved a far more meaningful and lasting form of permanence. There is a powerful lesson here for our own era, particularly as we grapple with the challenges of sustainability and environmental responsibility. Our current model of construction and demolition is incredibly wasteful. We build for a single, fixed purpose, and when that purpose expires, we often resort to the wrecking ball, creating mountains of landfill waste and expending massive amounts of energy to start again from scratch. The ancient model of cyclical renewal presents a compelling alternative. What if we began to design buildings not as finished, permanent objects, but as dynamic repositories of materials? Imagine a skyscraper designed with bolted joints instead of welded ones, with panels and beams that could be carefully disassembled and their components catalogued for reuse in the next generation of construction. This isn't science fiction, It's a return to a very old idea, now amplified by modern technology. We could create a circular economy for the built environment, where the concept of waste is designed out of the process. The intentional weak points of the ancients find their modern parallel in design for disassembly, where the end of a building's life is not a violent conclusion but the beginning of its next chapter. This shift in perspective requires a fundamental change in how we view our own creations. It asks for a humility that recognizes our place within natural cycles, not apart from them. It encourages us to think like the Maya temple builders, who saw the old structure not as obsolete, but as the sacred and stable foundation for the new. It invites us to adopt the Roman engineers' foresight, who built for the maintainers of the future they would never meet. By letting go of our obsession with rigid permanence, we might just discover a more resilient, adaptable, and truly sustainable way to build. The silent, stoic ruins of the ancient world are not just relics of the past, they are blueprints for a more thoughtful future, reminding us that sometimes the greatest strength is found in knowing how to yield. Unlocking the secrets of these ancient engineered failures requires a modern detective squad, a fusion of minds that would have been unthinkable just a few decades ago. Today's breakthroughs don't come from a single brilliant archaeologist with a brush and a notebook, but from a collaborative symphony of experts speaking very different technical languages. The field archaeologist who can read the story in the soil layers now works side by side with the materials scientist who can analyze the atomic structure of a 2,000-year-old mortar sample. The structural engineer who designs skyscrapers runs complex computer simulations on the load-bearing capacity of a Maya corbel arch, while the cultural historian deciphers myths and royal inscriptions that might explain the ritual purpose behind a specific collapse. This isn't just a team effort, it's a complete reinvention of how we investigate the past, where a sample no bigger than a grain of rice can reveal a world of intention. The tools at their disposal are nothing short of revolutionary. Take 3D laser scanning, for instance. A team can now set up a scanner in a dark, cramped chamber deep within a pyramid, and within hours, they have a perfect millimeter-accurate digital twin of the entire space. This model can then be rotated, sliced, and examined from every possible angle on a computer screen halfway across the world. They can perform virtual measurements between stones that would be physically impossible to reach with a tape measure, searching for patterns of wear or intentional gaps that are invisible to the naked eye. This digital record is then fed into engineering software for finite element analysis, a process that allows modern engineers to apply virtual stresses like earthquake tremors or the immense weight of settling stones to see exactly how the structure would behave. They can test their theories digitally. What happens if we weaken this specific lintel? Does the stress redirect as we predict? Does the failure propagate inward to protect the main chamber, or outward, causing a catastrophic collapse? This digital sandbox allows them to experiment with ancient designs without ever touching a stone, turning hypotheses into demonstrable mathematical probabilities. The analysis goes even deeper to the very chemistry of the materials themselves. Using portable X-ray fluorescence spectrometers, researchers can now point a handheld device at a mortar joint and get an instant readout of its elemental composition. They can quickly compare the mortar used in 99% of a wall to the curiously different mix used in one specific critical joint. Was it made with more sand? A different type of crushed brick. These are the telltale fingerprints of intentional engineering. In laboratories, thin sections of stone are examined under powerful microscopes to study their crystalline structure and how they would have reacted to centuries of stress. This molecular detective work separates accidents of time from the original blueprint, proving that a weakness was baked in from the very beginning. This collaborative, high-tech approach is systematically dismantling long-held assumptions about technological progress. For generations, the narrative often implied a linear march of innovation, with ancient methods being necessarily more primitive than our own. What this interdisciplinary research is revealing is that different does not mean simple. Ancient engineers may have lacked our computational power and material science vocabulary, but they possessed a deep, intuitive, and practical mastery of physics that they applied in astonishingly sophisticated ways. They were asking different questions and had different priorities, often blending the physical and spiritual into a unified whole. A modern engineer aims for maximum efficiency and safety. An ancient Egyptian engineer aimed for eternal preservation aligned with cosmic principles. Their solutions, therefore, look different, but the underlying intelligence is just as profound. This new way of seeing reminds us that human ingenuity has always flourished in diverse and brilliant forms, and that the silent stones of the past still have profound lessons to teach us if we only have the right tools and the right teams to listen. The discovery that ancient builders intentionally designed collapse points into their structures fundamentally revolutionizes our entire understanding of historical architecture. We can no longer look at a pile of rubble at an ancient site and simply see the aftermath of decay or disaster. Instead, we are learning to see the signature of a master architect, a deliberate instruction left in stone for how the building was meant to transform. These features were not flaws in the design process. They were the design process sophisticated, multi-purpose elements engineered to serve a complex web of ritual, practical, symbolic, and protective functions. This revelation forces a complete paradigm shift, moving us from a view of ancient builders as creators of static monuments to visionaries who designed dynamic, interactive systems meant to evolve over centuries. This practice unveils a mindset that is profoundly different from our modern approach to construction, where we often strive for linear permanence, building with materials and techniques intended to resist change indefinitely. These ancient engineers thought in cycles. They saw their creations as participants in a great, ongoing dance with nature, time, and the divine. Their ambition wasn't to defeat these forces with unyielding strength, but to collaborate with them through intelligent design. They integrated spiritual significance with practical necessity in a way that modern specialization has largely forgotten, creating structures that were at once temples, calendars, community centers, and sophisticated machines for managing physical forces. This holistic perspective allowed them to plan for transformation rather than futilely fighting against it, building with a humility that acknowledged their place within vast natural cycles. As we confront our own global challenges with sustainable architecture, resource management, and cultural preservation, these ancient approaches suddenly feel incredibly relevant and urgently modern. Our current model of build, use, and demolish into landfills is a linear system on a planet that operates in cycles. The ancient model of architectural renewal, where a structure is designed from the outset to be taken apart, its materials harvested and revered for reuse in the next iteration, presents a powerful alternative. It's a blueprint for a circular economy that was perfected millennia ago. It asks us to consider designing buildings not as permanent, finished objects, but as dynamic repositories of value with components that can be disassembled and repurposed. This ancient wisdom encourages us to build with both our grandest ambitions and our deepest humility, creating a legacy that is resilient precisely because it is adaptable. Ultimately, these intentional weaknesses are far more than clever engineering tricks. They are windows into ancient minds, offering us a glimpse of how entire civilizations conceived of their relationship with time, with their community, and with their place in the cosmos. A deliberately weakened lintel stone is a philosophical statement about the necessity of change. A chamber designed to collapse in an earthquake is a lesson in redirecting energy rather than absorbing it. A temple sealed with ritual rubble is a covenant with the future. By learning to read this hidden language of stone, we don't just uncover the secrets of the past, we find timeless principles that can guide us toward a more thoughtful, resilient, and sustainable future, reminding us that true endurance is found not in rigid defiance, but in the wisdom of graceful